Okay, let us see. Let us see how in the matrix. Okay, we'll just say use the same similar kind of example that we discussed last class. So what we do is I want to show you that real numbers, like you already know, are rounded off, are sometimes rounded off. You cannot continue 1/3 like 0.003, 0.333, round it off, or you have to truncate. Now I want you to show that number of digits which you are using in this coefficient of the matrix in your calculation can have a significant effect. So, and Gauss elimination can also fail when one of your matrix element is 0. Okay, that we will see how it fails. Anyway, so let us start with one example. Consider this matrix. You know that any system of linear equation can be written in terms of Ax equal to B, isn't it? Fine. So I am writing the matrix A for you. A very tiny number. Can you solve for x1 and x2? Okay. What we basically do, of course, you can easily do this because it's a 2 by 2 matrix. But what we learned in last class, our aim is to make this element 0. Our aim is to make this element 0. How can we make this element 0? We can make use of the combination of this equation and this equation. Okay. How we can make use of the combination? What can we do? Same thing, like you multiply, this is equation 1, this is equation 2. Okay, what I am telling you, equation 2, change it in this way. How can you change? Minus 1.0 by 3 into 10 to the minus 4 into equation 1, fine, plus equation 2. If you do this, can you visualize what is happening to this element? This element is transforming to 0. And similarly, this element and this element will also get affected. This and this will get affected. Okay. How it gets affected, can you tell? So what we will get, if you do that, the first equation remains unchanged. We did not touch the first equation at all. And x1 and x2 solution are still the same. Nothing happens to them. The right hand side, the first element is still the unchanged. But the second equation will change according to this rule. Now how? I am multiplying this quantity 1, then I am adding it back to equation 2. Can you see this element is 0? Can you visualize that this element is 0? Then what happens to this? This element will be 1.0. Sorry, maybe I'll follow the pattern. It will be minus this into this. So minus 1.0 by 3 into 10 to the minus 4 into 3.0 plus you are adding equation 2, which is 1.0. Isn't it? Fine with you? Then what happens to the right hand side? The right hand side gets minus 1.0 divided by 3 into 10 to the minus 4 into equation 1, which is 2.0001. Then I'm adding equation 2, which is 1.0 again. Fine with you? Now can you tell me what are these numbers? So I'll write it for you. So is this correct? Is this correct? Is this correct? Compute a bit. So you can easily get x2 from the second equation. From the second equation, you can easily get x2. So from the second term or second equation, we can get, can you multiply 0 into x1? So we get 0 into x1 minus 9999 x2 multiplied by x2 equals to minus 6666. So x2 equals to this number, isn't it? Yes. Now what is x1? This you did forward elimination. You are going all forward. You never went backwards. After you got x2, now you go into the first equation, substitute x2, use the backward substitution, get x1. What is x1? So we have the equation of x1 as this, plus 3 into x2. x2 is equals to 2.0001. So x1 equals to 2.0001 minus 3 times this quantity divided by 3 into 10 to the minus 4. Yes, agreeing with me till now. Or maybe better I would write, this is x2, so I will just write it x2 because I want to do an experiment. Let me write x2. So just you have to put this x2 over here into here so that you get the solution. x2 is just like, can you tell me what should be the x2 value? Now let us do this experiment over here. Let us do this experiment. Maybe let us write x2, let us write x1. x2, can you check using your calculator that x2 can be this? Yeah, something like that, 0.6666. Now I am going to tell you what this small tiny decimal can have an effect on the solution. Let us take x2 to be 0.667. Let us take x2 to be 0.667 and you substitute that value of x2 over here. Can you tell me what x1 you are getting? We will take 3 such quantities. You can see these are very close to each other, isn't it? Depending on this formula. Can you tell me quickly? Column can do for first 0.667. The second column can do it for 0.6667. And the third, you guys can, this whole column can do for the last one. Which one? Last one is 0.3. Minus 3 you're getting. Oh, exactly. It's not minus 3.33. Okay, you can do the second one. Second one, this column should do. Oh, this column, I will ask randomly. Yes. Ready? Randomly I will call. Second. Who will come? Who will volunteer? This column got anyone? Anyone got who? Which one? Okay. -3. First one. First one. Okay, then. Yes. So can you appreciate this? Can you appreciate this? So many different students came up with the same answer, but you can see how the small tiny effect of these almost same looking equations, same looking numbers can give you hugely different outcome. Okay. So yeah, so this is what I mean. Why this is failing? First of all, why this is failing? First of all, it is failing. This method is failing. Why? We so many laugh. So happy. Why? And they're happy they won't even look up. They will look down only. You only. Yeah. Okay. So what I'm telling you is why this method is giving such nice outcomes, like in such a way that just tiny change in decimal places is giving you huge change in outcomes. Is mainly because your element is very small here. It's tiny element, very tiny element. Okay. If you face this kind of equations, I strongly suggest you swap it. Swap it. Swap the rows. If you swap the rows, does the solution change? If you swap the rows, I mean like whatever is written in the second row, transfer it to the first row. Whatever is written in the first row, transfer it to the second row. If you do that, will the solution change? Everything you are swapping. It's not like only this and this you are swapping. This one also you are swapping. Will the solution change? What does your brain instinct tells? No, it's just that you are writing. It's just that you are writing the first equation in the second place and second equation in the first place. You're just writing the position change, nothing else. So if you face some kind of this situation, how to avoid this situation? You can avoid this situation by just swapping it. Okay? So this we call it as a row swap. So if you do a row swap, just tell me like what are the variables you are getting. I have to look again now. If you do a row swap, what you get? Can you tell 1.0, 1.0? The here? Here? Yes, because it is. Is it? Is it? I think I told you a mistake. I think I told you a mistake and you also agreed to it. That is what, like, you should ask the question, you should stop me. Like, your brain should exercise. See, I told you that I will also swap this, and you felt that yes, it is okay. But if I swap this, everything changes. The whole equation changes, isn't it? Why? Yes, this quantity which should have been multiplied with x1 will now get multiplied with x2. Suppose this is the same element. Let us not take this one. Consider the first row. Consider the first row. If the first row is coming down and this one is going up, this guy is multiplied with x2, not x1. If you swap the x1 and x2. Are you seeing it? So therefore, can you don't blindly follow me? Okay. I suggest, like, please be kind of attentive in the sense that put your brain in a faster mode. Okay, put more course into the class. Okay, so let us see. So what we should do here, it stays the same. What happens to the other side? that will swap, of course. Okay. So what's the swapping? 2.001 is it? Yes. If you do this quantity now what is the factor? What is the factor now? Can you see this? This will be the very beautiful transition now for this problem. So what you do now? Same equation 2 will be divided by 1.0 times equation. What we have done here? Equation 1. Yes. Equation 1 plus equation 2. Same thing we are doing. And the same way, I suggest try this. You will get, if you do this process, you will get to this form 0.9997. The x1 and x2, of course. This is, and 1 will be remaining unchanged. This quantity will change because of the transition, like the equation change. What it will change, can you tell? It will be something less than that, because the minus of this is getting added to minus 2.001. Can you tell me what we should get here? The thing is equation 1. So what is the value of 2.001 minus 3.0 into 10 to the minus 4? Should be less than 2 point something. This one. Okay. Yes. Can you see that? Now you can compute. Now this is 0. So you can compute x1, x2, sorry. After that, do backward substitution and get x1. What you get x2 and x1? Now, if you do the same experiment, I suggest this you try. Okay. This you try strongly now. Let us do the same table now, x2 and x1. Okay. x2 and x1. x2, previously we took 0.667. Here also we will take something like that. 0.667. 0.66667. Okay. Then we will take 0.3457. All this variable you take, like last time. Then I suggest you find what is x1 in all the cases. Find x1 in all the cases and compare with the previous method, with the previous solution. Can you do this within 2 minutes? Try to, like, because everything is there. Okay, let us be back. Yeah, let us be back. So can you see this example over here? What we saw from here? Can you see now that the solution is almost converged? Can you appreciate that the solutions are almost converging? Why did not happen? Same equations did not happen. Same equation when we took this, you see, it almost gave small tiny changes, giving you huge output difference. Why this happens? Can you know? Can you tell me? Just one line. One line you should tell me why this happens. But that's not the issue. The issue is more deep. There is a small element, fine. But it is something you are doing with that small element matters. Yeah, exactly. Exactly. That's very good. So I wanted some of you to understand it. See, the small element is there. That is a problem, of course. But This we saw that here also the small, but we are approaching a good solution. But why in the first case we failed? It's because it's more detailed than that. It's because when you are considering the pivot, okay, this is not something known as pivot. You are dividing by that small element. Since you are dividing by that small element, it is causing huge trouble to you. This case, we are not dividing by the small element. Why? Because we have swapped it. Because we swapped it, therefore the small element is now coming in the numerator. It is now coming in the numerator. So therefore you are not having the problem of division by the small element. So you see, both are the same problems. It determines how efficient are. So therefore, if in realistic situations you encounter a small element, okay, and in that small element, how you can manage that small element? You have to swap the rows so that when you multiply this quantity, the small element comes to the numerator. Got the idea behind this? So this, I think, is a very nice example of showing you small elements play a huge role in this Gauss elimination method. Okay, initiated it. So let us see. So we are learning through examples. If I had shown this via a theorem or some statement, then it is very difficult to understand. But I just showed you by an example. So this is what we learned in Gauss elimination method. This is all about Gauss elimination method. What does Gauss elimination method do? Forward elimination. Yeah. That then you do the backward substitution. Okay. Then most importantly, what you do, convert that coefficient matrix into upper triangular matrix. Okay, that's one of the most important things. Okay, the tiny observation has led scientists, even engineers, and even whatever you can call them, like people who are practicing this method, to know about the decomposition of matrices. This helped them think that since this is working, maybe if we decompose the matrix into a lower upper triangular, maybe the method will be faster. Hence, there is a term known as LU decomposition, and this small observation, which is converting to upper triangular and converting the matrix to lower triangular times upper triangular, is indirectly fed inside the packages of Python. So you can see where a small, tiny observation of yours can lead to an entry to the package in Python, which everyone in the world are using. Just a small observation. So those small observation matters. That's what I'm telling you. I think Miss Durga and Mr. Harishankar, they Hari. Yeah, so they found something. They made a discovery. They are saying so. We will see. We don't know. We don't know. So we want to discuss this. So yeah. So at the end of the class, we'll call them and they will explain us. Okay. So now we will look into something, some another method, but it's very similar to the Gauss elimination method. I'll tell you how it is. But before that, shall I? Yeah, it is something known as a Gauss Jordan method. All right. Okay, so Gauss Jordan method is nothing new. Okay, it's nothing new. It's just a variation. It's just a variation, another variation of method. It's a variation. How it's a variation? So in Gauss elimination method, you were just removing one unknown from one equation. Okay, that was leading to a triangular matrix, an upper triangular matrix. Okay, But in Gauss Jordan, if you eliminate x1, suppose, then you eliminate x1 from set of equation. In every line of equation, x1 won't be there. Okay. In next one, x2, if you are eliminating next step, x2 will be eliminated in all the equations. Okay. Do you think it was the case during maybe I will show you. It was not the case. Appreciate yourself that it was not the case for Gauss elimination. Okay. So major difference is that when an unknown is eliminated in the Gauss Jordan method, it is eliminated from all other equations, okay, rather than just the subsequent ones. Okay. So that's the difference, main difference of Gauss Jordan. And moreover, the rows are normalized by their pivot elements. Okay, the rows are normalized by the pivot elements so that you will get the diagonals will be mostly ones. Okay, so let's not worry about it by the statements. Let's just consider an example and work through the example to appreciate this method. Okay, I will tell you so far these two methods which we learned today, Gauss elimination and Gauss Jordan, these are not iterative methods. They are the iterative methods. Do you think? Are they iterative methods? No, because we are just directly solving. These are direct methods. Gauss elimination and Gauss Jordan method, which you are learning right now, these are not iterative methods. These are direct methods. Multiply the linear combination, just get the solution. These are not iterative method like bisection or Newton-Raphson method, where you need an initial guess and you keep on iterating to go to the solution. So therefore, we will discuss these two methods. Okay. Then I will tell you the need of iterative method to solve this. Okay. Let us solve one problem based on Gauss Jordan method, so that you can better know what is happening with this method. Okay. Then I will tell you the theory behind it. Consider this example. Solve this simultaneous equation. Okay, so using Gauss Jordan method, solve this system of linear equations. How shall we proceed with this? So in this kind of method, you will see that the Gauss Jordan method, Gauss elimination is a bit faster than the Gauss Jordan method. But it's usual for you to learn this method, even though it is slower, just to see the variation of this method. What we do, can you appreciate that you can write this in the form of Ax equal to B? You can write. Okay. Now, I will introduce you something new. That if you have the matrix A and you concatenate, do you think this is a vector, isn't it? This is also a vector, but this is a matrix. What I'm asking you right now is to create a new matrix by concatenating the matrix A with the vector B. Don't worry about the unknown X. Just whatever you have the known quantities, take them. Matrix A, then you concatenate, that is the symbol, and B. This is a new matrix, isn't it? You are adding one column. Are you okay with this? So matrix A, what I am doing in the matrix A, I am just padding it with B vector, column vector. That's it. That's how I am creating this new matrix. If you are padding up right hand side vector to the matrix A, you are creating something which is known as an augmented matrix. Now we will deal with this augmented matrix in this Gauss Jordan method. The aim of Gauss Jordan method is to transform the equations, transform the matrix. Here the matrix, can you tell me? Here what is the matrix? 3 minus 0.1 minus 0.2, 0.17 minus 0.3, 0.3, 10 times x1, x2, x3, and then you have the b, 7.85 minus 19.3, 71.4. Okay, got this idea? What I'm telling you, create an augmented matrix. What should be the augmented matrix? The augmented matrix looks like the augmented matrix. How the augmented matrix looks like? The augmented matrix looks as 3 minus 0.1, 0.2. Let us write the A matrix first. Then I'm concatenating this B vector onto the right. Okay, let me denote it as something blue. So 7.85 minus 19.3, 71.4. Now this is the augmented matrix. Can you see it? Okay with this? All right. Now notice this is not a square matrix. This is not a square matrix. Our aim in Gauss Jordan method, is to do the row operations in such a way that you convert this into an identity matrix. Get it? What are we doing here? Okay, this is the idea of Gauss Jordan method. Do the row operations in such a way, use the linear combination on row operations in such a way that you convert this A matrix, which is in the black, to this identity matrix 1 0 0 0 1 0 0 0 1, all ones in the diagonal, 0 elsewhere. And then the same operations you should do with the last column. No issue is there. It will change, of course. But then this star element which you will get is the solution. Is the solution you are looking for. Is the solution x1, x2, x3. So with just this simple operation, you are solving this system of linear equations. You can appreciate this method. Now, why this method works? That is detailed. Okay, that is detailed. I will tell you a bit of hint why this works. Is because you are converting a matrix A into an identity matrix through some operations. That will only happen. It's like you are finding the inverse. You are multiplying the inverse in some way. Okay, and isn't it? If Ax equal to B, then you can find X as A inverse B. Okay, that means you have I times X, and X here, isn't it? The same you have here, I and X. So you can see, you can make a communication, you can make a correlation between the methods here. Okay. So we are not going into deep why this method works, why this is going to fail, why not fail. All this will be like theorems, which is not our thing here in this course. Our job is to mostly see the methods if it is working, and if it is working, how to implement computational tools and using computer. So I told you the method here. This is the method for the Gauss Jordan. This is the method here. Okay. Now we use this method into this example. Ready? So let's start. No? Let us start. So what we should do? What we should do first? Your first aim should make this element 1. Make this element 1 so that you have this 1 over here. Okay, how you will do this? Divided by? Yes, do. So what you will get? You should work with this augmented matrix. If you do, what you get? So this 3 has some name to it. This 3, like I should give respect to this element also. Like should not tell 3. This 3, this 7, this 10, all these elements are known as pivot. Okay. So these are known as the pivot elements. So what we are doing here is normalizing the element by dividing it by the pivot. So if you divide it by 3, you will get 1. So what are you getting here? Can you tell me? 1, then minus 0.003333, something like that, right? Then, no, minus 0.06. Okay, then what happens to the 7.85? 2.6166. Okay, okay, good. So now the remaining elements, let us keep the same. Okay, let's not disturb this. Okay. Now what should be our aim? I told you in Gauss Jordan method, it is different from Gauss elimination method in the sense that if you eliminate x1, you eliminate x1 from all of the equations. So since you have a 1 here, now your job should be to eliminate this and this. Okay. This is multiplied by x1, isn't it? This is multiplied by x1. Each element is multiplied by x1. So if you put this quantity 0, then it is done. So this is the difference between Gauss elimination and Gauss Jordan. In Gauss Jordan, instead of just this to be 0, you do both of them to be 0. How you can do? You have to use some linear combination. Which linear combination should you use? How about row 2 is minus 0.1 times row 1 plus row 2? That does the second element goes to 0? Yes. For row 3, what you should do? Minus 0.3 into row 1 plus. Do you think if you do the second operation, this one is going to 0? Are you able to see the thing? Now, if you do this operation, this matrix transforms to which matrix? Can you tell me? To do this operation. Okay. So after we obtain this matrix, our next job would be to get the second column 0, 1, 0 matrix. 0, 1, 0 vector. How we will do it? So you know this, we have a 1 here, we have a 1 here. Okay. So how we will get 1 here? Divide by 7.0033. Convert it, and then you should apply. Then you should again apply the combination, isn't it? So after you eliminate it, can you tell me just by dividing? First row will be the same. It won't change. So I'm dividing by 7.03333, you know. 1. What are these two quantities? You have to tell me. What are these two elements? Mm, let us say again minus 0.188 and this one minus 2.36. Okay, so this is what we got, isn't it? The new matrix. Here you can see now that this is also 1. This element is also 1 here. What should be our aim next? Our aim should be to make this and the other two corresponding elements to be 0. So what you should do? What operation shall we do? So we should do operations on. So now R1 should change and R3 should change. In what way? R1 should change such as so you can do say 0.0333 into R2 plus R1. Fine. Then can you claim that this element is going to 0? Yes. R3, how can we do? Same thing. Minus 0.19 plus 0.1900 into R2 plus R3, isn't it? If you do that, what matrix you get? Okay. Okay, so I will keep this for you to do. But I will show you what are the steps here. So this will be in the notes which I will share with you today. So you are I think you are getting a feel of this method, what we are doing here again and again, isn't it? So after you do that, then what will happen? This will be 0, 1, 0. Then this column will be remaining. This column will be remaining. You have to do in a similar pattern. This one. Got the idea? So if you do the calculation, I think if someone might have done already, I think you will get this equation, this matrix. Check whether you are getting this quantity. So after you got this quantity, look into your goal. Look into your goal. You covered the first and the second column of this. It looking like the same. Now you only have to do the third column over here, 0, 0, 1. So what you have to do here? So you have to make this as the pivot element and divide by the same quantity to turn it to 1. Okay. So in this row, just divide by the 10 and to convert it. So the rows, the two rows will be the same. Okay. But the third row will be changing 0, 0, 1. And then this one will be also divided by 10 point something. which you'll get around 7.001 or something like that. Okay. Can you appreciate this method now? Shall I write this full or? Can you appreciate this now? So it looks like this. Now what should be your row operation? Now your aim should be to make this and this guys to be 0. Okay, so row 1 and row 2 should be changed. Row 1 should be changed and row 2 should be changed. How? What you should do? You should do row 1, you should do 0.06806 times row 3 plus again row 1. Are you getting 0 here? Yes. Again, what you should do here for the row 2, 0.04188 times row 3 plus row 2. See, very intelligently and cleverly, I saw the negative sign here, then straightforwardly I took positive signs here, so that when added, they turn out to be 0. I did not get confused for whether I should use negative or positive. I straightforwardly saw negative, then I used positive, opposite. So if you do that, then what matrix you will get? This leads to what? This will lead to your solution. Okay, why? Because now you transformed your matrix to this form, isn't it? And whatever you are getting on the B vector on the right hand side, the column is the solution that we will get as something like this. So after you get this matrix here, this is your identity. This is your identity matrix. Whereas this is your solution. Now, can you do one more thing that, oh no. Yeah, can you do a thing here that check these, check that x1 is 3.000, x2 is minus 2.5, x3 is 7.001 is actually a solution. You can plug it back into your equation and confirm whether it is right answer. Okay. And observe that this Gauss Jordan method, which we discussed right now, no more back substitution method was done. It was always forward. Never we told that you got the solution, now substitute it back to the first equation. Did we do anything like that here? So it is like totally forward. Okay. But however, Gauss Jordan is more time consuming than that of Gauss elimination method. Okay. People have how I am claiming this is because each multiplication, how many times you have done the multiplication in Gauss elimination method, how many times the row operations you have done, how many times multiplication addition is done. In both of the methods, it is compared in terms of the size of the matrix, and it is found the number of operation in Gauss Jordan is more than the Gauss elimination. So of course, Gauss Jordan will be slower than Gauss elimination method in terms of computational time. So if you run a code, you can also do this. Write a code for Gauss elimination and Gauss Jordan and check which one is efficient. Okay. For any kind of matrices. So hope you got the difference between the Gauss elimination and Gauss Jordan method here. Remember, in Gauss elimination method, you were converting the matrix to an upper triangular matrix. Here, what kind of matrix are you converting it to? Identity. So that's the difference. Moreover, you are not using back substitution method like Gauss elimination. In Gauss elimination, once you get the x3 value, you substitute it back to get x1 and x2 previous values. Here you are getting all at once. Okay, so these are some of the differences between the direct methods discussed here, Gauss elimination and Gauss Jordan. Two popular methods, direct methods. So these are, you can see, these are a bit time consuming methods. These are a bit time, should appreciate them because you are doing it. Okay, these are time consuming. Now the idea is, think that this equation is pretty okay because you are doing 3 by 3 equations. But what if you consider a realistic scenario of optimization? I told you in the previous class that where you consider this traffic signals and you are trying to optimize the traffic in such a way that there is no stagnation of vehicles. Okay, in order to do that, of course, you will have inequalities, but suppose you are doing equalities there. So you'll have lot of different factors promoting to traffic. So this equation will not be this, it will be a huge set of equations. Okay, huge set of equations. Moreover, in management and the business ideas, okay, this is very useful. You have to maximize your profit. You have to maximize your profit, and your profit will depend on a lot of scenarios. Okay, will depend on a lot of scenarios. So therefore, automatically the number of equations and number of unknowns will increase. If the number of equations will increase, you can appreciate that you are getting a very big matrix. If you have a very big matrix for a large matrix, these methods will not work. Gauss Jordan and Gauss elimination method will not work. In order to solve huge amount of lot of heavy matrices, you have to use numerical methods, which brings us to iterative methods in solving these kind of equations. So there are two types. There are two types. One is Jacobi method, another is Gauss-Seidel, okay, which we will be learning. Okay, so yeah. Before going to the method, we